All right, so today we're going to continue with trees and tree-based data structures. Last time we kind of introduced some of these ideas and these definitions, and we're going to continue to, as we introduce more and more notions, what we were basically doing was adding more and more structure to our graphs, right? We start out with just general graphs where you've got vertices and edges and they can be connected in any old way. But what we wanted to do is we wanted to restrict our attention to trees, which are acyclic graphs. And the reason there is because between any two nodes, there's exactly one path from that node to the other node. And that adds even more structure. Now, ultimately, our trees are going to hold data. And so what we want is we want our nodes to be holding data, and so we want to organize them. So we want to orient them top to bottom and also left to right. That gives you a parent-child relationship, but it also, if you've got multiple children, you've got the first child, the second child, the third child, etc. And that adds even more structure to it because now you can start treating it like a data structure that holds pieces of data or keys or values or whatever you're trying to put into it. A few more definitions here. The length of a path is the number of edges in it. I think we did this last time. If not, that's perfectly fine. Let's go ahead and look at an example again here. Right? If I've got a tree, and I'll just draw these as little nodes here. Right? And there. Actually, could I add any one more edge here? Say that I added this edge right here. Could I do that and it would still be a tree? Nope. Could I add this edge over here? Nope. So what was another observation that we made last time? That there are 1, 2, 3, 4, 5 nodes, and there's 1, 2, 3, 4 edges. Can there be any more edges? Nope. The number of edges is exactly equal to the number of nodes minus 1. Any additional edge at this point means that you will induce a cycle, and so we can't have that. All right, so if I label these things, say A, B, C, D, and E, I can make the observation that I can go from A to D with exactly one path. Go to E first and then go over to D. The length of that path is 2 because I traversed 1, 2 edges to get there. What's the length of the longest path here? There are a couple. Right? I can go from A to C by going to E, then to D, and then on to C. Right? I could go from A to E to D to B, and that's also a path of length 3. Right? So there are notions of this path is longer than this path, and what do we mean by length? We mean that that's the number of edges in it. How many steps do you have to take from going from one vertex to the next vertex to the next vertex to get there? And we only consider simple paths, a path that only traverses edges exactly once. In this example, of course, I could go to E, to D, over to C, then back to D, and then back over to B, right? And that's an even longer path, but it's not simple because I traverse this edge here twice. Right? We're not going to consider complex paths. We're only going to consider simple paths. So once I've got a tree, remember the trick. You can go ahead and take any node, dangle it, and then it's all oriented top to bottom. So for example, if I dangled it from D and then shook out all of the values, what would it end up looking like? Here's D at the top. D would end up having 3 children, B, C, and D. Or sorry, not D, E. There we go. And off of E would be hanging A. Okay. Now what we can do is we can consider the depth of a node. The depth of a node U is the length from the path, the unique path from from the root at the very top down to U. Here D is our root. Remember, our trees grow downward, right? And so what you have what do you have at the end of trees? You have leaves, things without any children. What do you have at the root of your tree? Well, you have the root, right? Everything else emanates from it. But ours grow downward, so the root here is at the top. Okay. So what is the depth of, say, D, A, B, C, and E? What is the depth here? Well, let's take an easy one here first. What about A? The depth is the length of the path, the unique path, from the root all the way to that node. So the unique path is of length 2. And so what's its depth? 2. Right? Here's the node, and then here's the depth of the node. Oops. Thank you. Please go ahead and yell at me every time I do that. Sorry about that. Oops.
We can still see the tree.
Okay, good. All right, and I wanted to move that over there to get that out of the way. Thank you. All right, so A has a depth 2. What about B, C, and E? B, C, and E. They're all depth 1. What about D itself? Well, if this is of depth 2, this is of depth 1, then by convention, what is the depth of the root? 0. Right? And so you can have depth 0. Right? The depth of the tree itself is the maximal depth of any node in the tree. So if I look at this entire tree over here, what is the depth overall of the entire tree? You just take the deepest node, and that's the depth of the tree. Well, A here is the deepest node. It has depth 2, so therefore the depth of the entire tree is 2. Right? Now there are some corner cases here. What if I have a single node and no edges because there's no other there's no other node to connect to? We call this one year, we don't really have a general name for this, but one year somebody suggested that we should call this a seed because there's only one node, right? So what if there's only one node? What's the depth of that node? It automatically becomes the root. And so its depth is 0. And so the depth of the tree is 0. What if I have an empty tree? And that is certainly possible. You can have an empty set. You can have an empty list. You can have an empty array, right? Well, what happens when you've got an empty data structure where that data structure is a tree and it's empty? What is the depth of an empty tree? So the one before looked like this, and it was of depth 2. If we trim that out, if we prune it, and we had this tree instead, its depth is 1. We already said that the depth of a seed is 0. And so if you take this and continue with the basic idea, what's the depth of an empty tree? -1, right? And that's by convention, so that everything works out and everything is consistent, right? So an empty tree has depth -1 by convention. Now what we're going to do is we're going to add even more structure. A binary tree is a tree such that every node has at most 2 children, right? A left child and a right child. Right? Now it could be the case that you have a node with no children, in which case you have, what are those things at the end of the trees again? They're leaves, right? A leaf is a node with no children. A leaf is a node with no children. Right? A node, a binary tree node, may have 0, 1, or 2 children. And in the case where it has 1 child, you could have a left and not a right. You could have a right and not a left. So pictorially here, if I go back over to this over here, it is perfectly fine to have both children. It is perfectly fine to have a left child but not a right child, right? There is no right child here hanging off of this. It is perfectly fine to have a right child but no left child. The left child is missing. And it is perfectly fine to have no children. So it could have 0, 1, or the other, and or 2 children. Okay, that's what a binary tree is. There we go. And So what I want to do is I want to make a couple of observations now. Observations, right? Because of this restriction, there is a limit to how many nodes may be present at any level, right? Thus, there is a limit to a binary tree. Actually, no, I'm gonna hold off on that until we do this analysis here. So what do I mean by that? So let's go ahead and consider what's called a full binary tree. Let's go ahead and create a tree, a binary tree, such that all of the children are there except for the last level, right? So at the first level, if I maximize that, then there's a root, right? So here's my depth, 1, right? I'm going to spread this out here. There we go. And here's the number of nodes. Remember, I'll remind you at this point that we are online. If you have any questions, go ahead and post them to Piazza. Otherwise, how many nodes are there at depth, depth 0? We have the number of nodes being 1, right? Just that root right there. What about at depth 1? If I have both children there, then I have 2 nodes, okay? Let's keep going. What about the next level? If all the children are present, then at depth 2, we have 4 nodes. Let's write one more and count up the number of children that are there now. At depth 3. How many children do I have? 8. Right? Dot, dot, dot. At depth D, how many children am I going to have? How many nodes am I going to have at that depth? 2 to the D. Good. Right? You saw the pattern that this was 2 to the 0. This was 2 to the first. 2 squared. 2 to the third. Right? And if I just keep going here, then at depth D, I'm going to have 2 to the D children if they're all there. Okay? So suppose I have a tree in a tree of depth D, in a tree of depth D, how many nodes total are there? In other words, I want to sum all of these up right here. Okay? This is just a summation of I running from, where did we start over here? We started at the depth 0. So I will start at 0 and go all the way up to what? D. And we already came up with a general form at each level. It's going to be 2 to the D, or in this case, since I'm iterating on I, it'll be 2 to the I. Right? In other words, it's going to be 1 plus 2 plus 4 plus 8, just like I did up here, top to bottom though, plus dot, 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 2 to the D, where D is the depth of the tree. Okay? So I'm not summing natural numbers. I'm not summing 1, 2, 3, 4, 5, 6. I'm summing exponential numbers. I'm summing powers of 2. So pull out your calculus out, or algebra, or wherever it comes from, and tell me, what's the closed form solution of this? No? There is a general form solution for this for all bases, but, oops, I was just thinking of a different base. 2 to the D plus 1 minus 1. Right? Now let's just test that out. If I cut this off at 3, how many total are there? 1 plus 2 plus 4 plus 8, there would be 15, right? And that would have been at depth 3, so 2 to the third, or 2 to the third plus 1, remember we're plus 1 right here, minus 1 is equal to 15. Checks out. Now, why did I go through this exercise? In a full binary tree of depth D, with n nodes, we have that n, the number of nodes, is equal to 2 to the d plus 1 minus 1. That's the number of nodes. What I want to do is I want to get the depth in terms of n. So in other words, solve for d. I can take 1 onto the other side. N plus 1 is equal to 2 to the d plus 1. How do I get rid of that 2 to the? Take a log, base 2 of n plus 1, and then immediately subtract 1 to take it to the other side, and I've got my depth here. Right? In other words, i.e., d is going to be order log n. Right? Now, why is that important? Right? Here's my observation again. My observation is that if the binary tree is essentially full, then we have that its depth is order logarithmic. Why is that nice? If, now this is a big if, we can formulate basic operations such as find, insert, delete, update, right? The basic CRUD operations, such with performance that is proportional to the depth d, then all operations may have complexity order log n. Sound familiar? Order log n being, that's what we got. We started this at the very beginning, observing that we've got a quest here. We want to search for a data structure that can hold and provide efficient operations for retrieval and search, insertion, deletion, basically the CRUD operations. Linked lists, they were fast on one operation, but very slow on the other operation. They were linear on the other operation. Array-based lists, that just switches around on those, except for if it's sorted and we have an array-based list, we can exploit binary search on this. Now we're getting all 4 operations. If we can make these guarantees that it's essentially full or balanced in some sense, then all 4 of these operations are going to be basically performant, just as performant as binary search is on an array-based list. Right? Awesome. We're not going to get there yet. We're not going to get there in this class. All right. What you really want is a balanced binary search tree, but we are going to make efforts towards that goal. Okay. But that's why I went through all these observations. Like, if we can do this, then we've got a great data structure that provides very, very high performance on all operations. Okay. Before we do that, though, we need to talk about other basic operations. So, what about implementations? Say Java. How would you go about implementing a tree? Let me go back to my notes here. What did we do with the linked list? We had, I'll draw it like this. We had a series of nodes, right? And they contained an element, A, B, and a link or reference to another node, C, ... Right. So let's use that same idea. If I've got a tree node here with an element A, what references do I need? Remember, it's a binary tree node. A left child, a right child, and optionally, it's going to be really super convenient to have it, a parent reference. Right? So in other words, each node will have an element and 1, 2, 3 references, which could be null, right? If I've got if I'm referring to null here and a null here, right? Then what is that? That's a leaf, right? No children. What if I've got a node here that references a null parent? What kind of node is that now? That's the root, right? Otherwise, everything else will have a parent, okay? So let me go ahead and open up my Eclipse here and show you that I've already done this, right? Let's make sure that it's actually on the screen, right? I've already parameterized it. This is called I called it tree node. Of course, more accurately, it'd be a binary tree node because just in general, a tree node could have 50 children, right? So you would want an array or a dynamic collection to reference your children. So technically, this is a binary tree node. It has a value being stored that's parameterized. It's an element t. It has a left child, a right child, and a parent, which are all tree nodes parameterized on the same thing. So you don't have the case where you've got one node holds an integer and another node in the same tree holds a string or something like that. That'd be weird, right? And I've got a whole bunch of things here, a whole bunch of boilerplate, a constructor that you can put the value in, but then there's no parent, there's no left child, there's no right child. You can provide a value and then specify what the parent is. I've got setters and getters for the parent. I've got setters and getters for the left and right child. And I also have these convenience methods that tell me, does it even have a left child? Does it even have a right child? Does it even have a parent? Right? Is it a leaf? Right? Well, it's a leaf if it has no left child and it has no right child. Give me the value, give me a string representation of this, equals and hash code method, et cetera, et cetera, et cetera. So there's my implementation of a tree node. Now, before I reveal what is in the binary tree, what's in a binary tree? Right? So let's go back over here to this. Oh, yeah. Nope. I'll go ahead and draw a new binary tree over here. A binary tree, say, doesn't have to be full, right? You could have nodes with both children. You could have a node with only a left child. You could have a node with only a right child, like we've got right here, say. You can have nodes with both children. You can have nodes with no children, leaves. Right? There's a binary tree. It's certainly not full, though, because I am missing a whole bunch of children right here. Okay? How do I represent this in, say, Java? Do I keep hold of all 4, 5, 6, 7, 8? Do I keep a hold of all, what did I just say? 9 of these nodes in an array? Now, if I did, then you'd be all back at square one with a list, right? With a linked list, did I keep track of every single node? I only kept track of what? The head and possibly the tail. So with a binary tree, which ones should I keep track of? The root, and only the root. And that's what my implementation does here. I've got a binary tree. All I have access to is the root. All other operations will emanate starting at the root. Just like a linked list, all operations in a linked list started at the head or possibly the tail. Now you might be thinking, well, wait a second. If we keep track of the head and the tail in a linked list, why don't we keep track of the root and all the leaves in a tree? You could do that, but then again, you're back at square one. Essentially, you're keeping track of too many things. With a linked list, it's just one or two things. But if you kept track of all of the leaves, you could be keeping track of n divided by 2 things. Right? So we don't want to do that. I've also set this up so that I can create a tree. I'll show you graphically what that looks like here in a second. But otherwise, I've got a toString method here. I want to print the tree. Right? What's in this tree? This tree looks like the following. Let's see. Nope. There we go. There's the tree that I just built. Right? Is it apparent that that's what I built there? Nope, it was a lot of manual work. Right? So that's what it looks like, though. How do we know that it looks like that? So one thing that I want to do is, here's a Java implementation. Let's go ahead and review what we just did. You can define a tree node that holds an element and 3 references to other tree nodes, right? For parent, left, right, right? And then you can connect them appropriately like I did with this code over here to build this tree right here, right? That's just from the book, okay? So you can define a tree node that holds, and then you can, of course, the tree itself is represented simply by the root element, right? The root node, I should say, okay? So here's my first goal, first task. Implement some sort of traversal method, right? That is, just given the root, can you visit every single node at least once, right? So for example, can I take all the nodes in this tree and dump them to a list and ensuring that I can actually get to every node in the tree? Just like with a linked list, right? With a linked list, one thing that you wanted to do was you wanted to search through it. How did you do that? You started at the head. Is this it? Nope. Is this it? Nope. Is this it? Nope. ... until you get to the thing that you're actually looking for. With this tree, I want to search for, say, I. Search for I. Okay? That's right here, by the way, if you can't see it. But I only have access to the root. So ideas. Let me go ahead and change the scenario here. Let's search for J. All right. What if I started at A and said, oh, well, that's not it. Right? If I were searching for A, then I'd be done. Right? I got lucky. Right? Can you always assume that you're going to get lucky? No. Right? So now I have a path. Right? It's like being in an alley, and I've got, or it's like being in a maze, and I can go that way or I can go that way. I can see the entire tree right now, so I know that I need to go that way. But in general, can you see the entire tree here? Nope. So, ideas. If you're in a maze, like I said before, what are you going to try? You're at a restaurant now and you're waiting for your food and you've got the maze sitting in front of you on the kiddie menu, right? You need to get to the end somehow, so what do? You try this direction. Oh, dead end, that didn't work, right? And then you come back. Then you try the other direction. Right? So what we're going to do is we're going to traverse down to the left subtree. Left subtree. And of course we're going to end up searching the entire tree, finding that there is no J in that left subtree. And then what we're going to do is, well, okay, well, that didn't work, so I'm going to go ahead and try and go down this tree, this right subtree. Search for what I'm looking for. That's just the general concept, right? Once I get there, how do I make another decision? Well, first of all, if I'm at C, do I have a decision to make? Nope, I'm in the maze, and you could just go forward. All right, so go forward there. All right. I will apply that same reasoning, right? And this is not what I'm looking for, and I've got 2 choices. I'll try down that corridor, and if I'm successful, great. Otherwise, I will come back over here, and then I'll try down that corridor, right? And once I go left to the left subtree, I immediately find what I'm looking for, and the search is done. We can't always be that lucky, though. Right? So what we need is a systematic way of approaching this problem. Okay? Let's think about it in general. Let's think about it as being, I'm at a current node U. Right? I must have gotten here somehow, right? I must have come from some parent. Right? Now, I potentially have a left child and a right child, okay? I'm at the current node. I need to answer a couple of questions. First of all, is this the thing that I'm looking for, right? So, is the current node what I'm looking for? If yes, I can stop. I'm done. Right? Otherwise, else, if. I'll say it like this, if. Else, what should I do now? Pick a path. And since we read top to bottom, left to right in English, which path do you want to go to next? Go left. Traverse left. Right. If I don't find what I'm looking for, eventually I'm going to come back up the tree, right? Just like if you're in the maze and you hit a dead end, what do? You backtrack, right? You came back to where you came from. Hopefully you've been keeping breadcrumbs so that you know where you came from. If not, then you're like Hansel and Gretel after their breadcrumbs have been eaten and they're gone, right? And you don't know, now I'm trapped in the maze. I don't know where I came from, right? I don't know where I'm going anymore. After I'm done with that, I will traverse right. So what I want to do is I want to generalize this even more. Right? I'm not simply going to look at the contents of A. I'm just going to simply process the current node. Then go left, then go right. What does this mean? Well, like I said, the process could be you're searching for a particular needle in a haystack. It could be that you use that in some other call to another algorithm, right? I want to keep it general and generic. So here's the idea. Order traversal. At